Welcome to Module 19 of the Six Sigma Institute's Lean Six Sigma Certification Curriculum, which follows both the Council for Six Sigma Certification and the International Association for Six Sigma Certification Bodies of Knowledge. A full copy of the Council for Six Sigma Certification's Book of Knowledge can be downloaded from the course description section for free. In this module, we will be discussing the analysis of process correlation and regression. This module will take approximately 60 minutes to complete. At the end of the module, there will be a 5-question quiz on the topics discussed, which you can complete on your own at any time. You will also find several Six Sigma tools that you can download, including a correlation diagram template and a Pearson correlation coefficient calculator, both of which are Excel files. Correlation and regression are statistical concepts that help Six Sigma teams understand whether two factors within a process are related. You can use these tools to calculate whether an input is related to an output in some way, or even whether two inputs might be related. Correlation and regression are important to understand because it helps teams understand more about processes, analyze how elements of a process are related, and make predictions about the process. When two elements are strongly related along a linear line or even a curve, teams can create equations linking the two elements. This lets Six Sigma teams predict how the dependent element will perform if a change is made in the independent variable. Before moving forward, it should be noted that the analysis tool in this module don't assume normal data in all cases, but it is possible that very abnormal data can skew results. Before analyzing data, Six Sigma experts should always understand what type of data they are working with. Correlation is the linear association that exists between two variables within a process that is visualized through a scatter diagram. In this section, we will cover correlation and the linear association that exists between the two variables. We will talk about positive and negative correlation, the correlation coefficient, and how to calculate as well as chart this relationship using Excel and the Data Analysis Tool Pack. A positive correlation exists when the correlation coefficient is greater than 0, and it signifies that both variables are moving in the same direction. The two variables being compared have a positive relationship. That is, when one variable increases, the other variable moves in the same direction with the same magnitude. The degree to which the relationship is correlated, however, may vary over time, as they are almost never exactly correlated at all times. This correlation may be strong or weak. If it is strong, then a best fit line can be drawn along their path, and this information can be used to make assumptions about the future of the process if one variable reaches a certain point. If it is weak, then a best fit line can still be drawn, but it will not be as accurate. A negative correlation exists when the correlation coefficient is less than 0 and indicates that both variables are moving in the opposite direction. That is, it signifies that the two variables which are being compared have a negative relationship, which is when one variable decreases, the other variable moves in the opposite direction with the same magnitude. The degree to which the relationship is correlated, however, may vary over time, as they are almost never exactly correlated at all times. This correlation may be strong or weak. If it is strong, then a best fit line can be drawn along their path, and then this information can be used to make assumptions about the future of the process if one of the variables reaches a certain point. If it is weak, a best fit line can still be drawn, but it won't be as accurate. As the correlation coefficient approaches 0, regardless of whether it is positive or negative, the amount of correlation between the variables reduces to nil. It signifies that the two variables being compared have neither a positive nor negative relationship. When one variable increases or decreases, the other variable moves randomly in the same or opposite direction with different magnitudes. When there is no correlation, a best fit line can never be drawn, and it can never be used to make assumptions about the future of the process. Graphical analysis is useful to gain an idea about data relationships, and very useful for illustrating relationships to others. But statistical analysis helps teams understand relationships with more certainty. For the purpose of correlation, the statistical calculation we are concerned with is known as the correlation coefficient, or R value. The correlation coefficient is a number between -1 and 1. As the correlation coefficient approaches either -1 or 1, a relationship between the two variables is considered more likely or stronger. That is, if the correlation coefficient is equal to 1, then the relationship is certain, and all the data points in the set are found on the positive trend. And if the correlation coefficient is equal to -1, then the relationship is still certain, except that all the data points are found on the negative trend line. As the correlation coefficient approaches 0, regardless of whether it is positive or negative, the correlation between the variables grows weaker, and at 0, then there is absolutely no correlation between the two variables. There are several different ways for calculating the correlation coefficient, but in Six Sigma we generally use the Pearson's correlation coefficient. In Pearson's equation, you start with two columns of data with an equal number of data points in each column. You multiply the x from each row against the y in that same row. Then you sum, or add all of these products together. You add all of the x's together and add all the y's together, and then multiply both sums together and subtract the value from the sum of the xy products in order to arrive at the top number. It is possible to calculate the correlation coefficient using one of these formulas. But luckily today's technology provides digital methods for automatically calculating the number. You can use statistical analysis software or graphing calculators to arrive at the correlation coefficient given data about two variables within a process. But we are going to discuss how you can calculate the Pearson correlation coefficient using Excel. In order to calculate the correlation coefficient in Excel, we need to create a table, and we can go ahead and use the example from the book. We will need to create a table with the independent variable, in this case time, in column A, and the dependent variables in the succeeding columns. Now there are several different ways that we can calculate the correlation coefficient in Excel. And the first way is to simply use the CORREL function in Excel. So, in this part of the example, we are going to compare the time with the temperatures A and C to see not only if there is correlation, but also see how strong that correlation is. As discussed, one of the easiest ways to calculate the correlation coefficient for two sets of possibly related data is to use Excel's CORREL formula. Select any cell underneath the temperature A data and enter equals CORREL, open parenthesis, close parenthesis. Inside of the parentheses, we need to define two arrays of data. Array 1 is the set of cells containing data for time. Array 2 is the set of cells containing data for temperature A. You can select these ranges with your mouse, separating them with a comma in your formula. Once the array data is entered into the cell, hit Enter, and Excel will calculate the R value, the correlation coefficient for the two sets of variables. In this case, a 0.98. Remember, the closer to 1 or -1, the stronger the correlation is. Select another cell and use the CORREL function, this time comparing time against temperature C. Once you hit Enter, you will see an R value of 0.107, which is close to 0, which means that the correlation is actually pretty weak. We only consider correlation to exist if the R value is greater than 0.4 or less than -0.4. You can also use the Analysis Tool Pack in order to calculate correlation coefficients. So using the same data, we are going to calculate the R value, the correlation coefficient for time and temperature B. To do this, we select the Data tab above the ribbon and choose Data Analysis. When the dialog pops up, simply choose the Correlation option and click OK. A new dialog will then pop up, allowing you to choose the data and options for your correlation analysis. Simply click on the input box and select the inputs for the correlation analysis. Select the data from both the time and temperature B columns. Select the option indicating that your data is grouped by columns. If you selected the header rows in the input range, check the box for Labels in the first row. But if you did not select the header row, then there is no need to check this box. Select the option to output the results to a new worksheet and then click OK. Excel will then automatically calculate the correlation coefficient for you. In this case, the result will be a negative 0.98978, which means that there is a very strong correlation between time and temperature B, but that correlation is a negative one. Repeat the steps using the Data Analysis Toolpack, but this time select time and temperature D. Excel will calculate the R value as a positive 0.86. This is still a strong correlation, although not as strong as temperature B, but there is still a strong positive correlation. Once you know that your data has a linear correlation, you can conduct further analysis through regression testing. In this section, we are going to discuss regression and how it lets you create a linear model that helps you to predict how one variable might behave given changes in the other variable. We will create a regression worksheet and conduct a regression analysis using the Data Analysis Toolpack, and we will even discuss dealing with low correlation in a regression test. Regression lets you create a linear model that helps you predict how one variable might behave given changes in the other variable. Note again that the changes aren't always necessarily an indication of cause, only that the variables are intertwined in some way. When working with regression, we talk about the coefficient of determination, or the R2 value. The R2 value is literally the square of R, or the square of the correlation coefficient. The R2 value is a number between 0 and 1. The number tells us about the strength of the linear relationship between two variables x and y, while the R value tells us how likely it is that the two values are related in some way. The R2 value tells us how much the fluctuation in one variable, the dependent variable, or y, is related to the changes in another variable, the independent variable, or the x. In order to understand how regression works, we will use the same data that we used in the previous correlation coefficient example. If you recall, the correlation between time and temperature A was strong. We will look at that relationship on a regression model using the Analysis Toolpack in Excel. Begin by creating a regression worksheet using the data by copying the data table into a new worksheet in Excel. You should now have two worksheets with the same data table. The table should look exactly the same on both sheets. Since we will once again be using the Data Analysis Toolpack, select the Data tab above the ribbon and click on Data Analysis. The same dialog will pop up, and this time you will need to scroll down a bit to select the Regression option and then click OK. A new dialog for the Regression Analysis option will then pop up. Go ahead and click on the Input Y range box and select the data from the temperature column. Then, for the Input X range, you will select the data from the time column. If you also included the headers when selecting the data, you will need to check the Labels box. For the output, select New Worksheet Ply option, and under Residuals, check the box next to Line Fit Plots, which will create the best fit line automatically for you. Once this is done, go ahead and click on OK. Excel will automatically calculate the correlation and regression for you, since the regression coefficient of determination, or R2 value, is simply the square of the correlation coefficient, or R value. In the new worksheet, you will find a summary output with a number of interesting calculations, one of which is the analysis of variance, or ANOVA, hypothesis test. That is why there was a confidence level selection in the option. The multiple R value at the top of the summary is your correlation coefficient, and there is a strong positive correlation between time and temperature A. The R squared number is the coefficient of determination. It is 0.96, which means almost all the variation in temperature in this data set is related to a change in time. Because you selected the line, fit, plots box when creating your regression analysis, Excel has also generated a scatter diagram and a best fit plot. The chart shows all of the actual data points in blue and predicted data points along a best fit line in orange. Those data points are calculated by Excel using a formula created from the data. You can display the formula by making design changes to the graph. In order to display the formula that we need in order to predict the future relationship between the variables, we need to make some changes to the graph. So we start by clicking on the graph itself. Now, above the ribbon, you will see a Design and Format tab. Select Design and choose to add a chart element. Select Trendline and choose the More Trendline options at the bottom of the list. A new dialog will then appear, and you will want to select the option for the predicted trend line and then click OK. Then you will have the option to display the equation on the chart itself. The trend line and the trend equation will now both be visible on the chart. In this case, the equation is y equals 3.3497 times x plus 27.561. If you remember, the R2 value is 0.96, which means that our linear equation is going to be very good at determining the approximate temperature in our process as a relation to time. So, at 5 minutes, for example, our equation predicts that the temperature is 44.30. This is calculated using the formula shown and by replacing the x variable with the temperature you will want to calculate for. So, if we replace x with 5, then we get 3.3497 times 5 is 16.7485 plus 27.56 is 44.3095. But if we replace x with 25 minutes, then we get 3.3497 times 25, which is 83.7425, plus 27.56, which is 111.3035, which would be our predicted temperature if we let it go for 25 minutes, well beyond the data included in our set. In order to see how regression tests might look with low correlation, let us repeat the steps above with the data for temperature C, which, if you recall, had very little correlation between time and temperature. The correlation coefficient is only 0.107, so the coefficient of determination, the R squared, is 0.0116. That means that only about 1.16% of the variation in temperature is related to the time. If we go through and format the trend line the same as before, and include the equation, you will see just how little correlation there is and how unpredictable it can be. For a time around 3, the equation predicts a temperature of just over 40. But the actual temperature was 75. And that number doesn't just reflect an outlier. That might point to a problem of data collection or a temporary process issue. The data throughout the chart is skewed far away from the line, making it very unpredictable. Correlation and regression are useful tools, usually deployed by teams in the measure, analyze, or improve stages of a DMAG project. In this section, we will discuss the use of correlation and regression in a Six Sigma initiative. We will discover that the tools don't apply to all data and are not useful in all situations where they might be applied. With time, a Six Sigma expert develops the ability to decide which tools might be relevant given certain data and situations. Because Excel and other statistical analysis software make it easy for Six Sigma experts and teams to play with the data in various graphical and statistical analysis, there is no harm in creating correlation or regression analysis for data in order to explore connections between variables. This is true as long as you are careful about what conclusions you draw. When in doubt, it is always best to back conclusions up with multiple types of statistical analysis. Both correlation and regression work with continuous or ratio data, and both sets of variables have to be quantitative in nature. For example, you cannot have X variables that are the names of people and Y variables that are the number of outputs. This type of data would not apply to regression and correlation analysis, but may be analyzed using tools such as Pareto charts or pie charts. Correlation requires two quantifiable data elements, and regression requires that data can be written as a function of y equals f times x. Distance, substance, hardness, temperatures, and even body mass index can be written in this way, and thus can be used in correlation and regression analysis. Correlation and regression can be applied at a number of points in a DMAG process. During the analyze phase, teams can use these tools to help verify relationships between inputs or to help bolster understanding of root cause analysis. While correlation and regression don't prove causation, they do not negate causation either. A strong correlation does not prove causation, but if a team already believes causation is a factor, then a strong regression model helps to validate that assumption. This is especially true if a team couples regression modeling with trial and error hypothesis testing. For example, a Six Sigma team might conduct brainstorming and fishbone diagrams, coming to the conclusion that a certain input, A, is causing variation in an output, B. The team's Six Sigma expert conduct regression testing, which shows that the variation in B is definitely related strongly to variation in A. The team can remove A from the process or alter A in some way and measure the process again. The team can then use hypothesis testing to determine if their changes created a statistical difference in the output.